Okay, today we're going to be learning about rotational statics. And in particular, we're going to be learning about rotational static equilibrium. So, static equilibrium, in the sense that we've been talking about thus far, generally meant that we had some object where all the forces acting on it added up to be 0. And as a result, there was no net force, so the thing was not in motion. And this is actually referred to as translational static equilibrium. Okay, but today we will probably be using some concepts from translational static equilibrium or translational mechanics, but today we're going to be looking at rotational mechanics, or in particular rotational statics. So when things are not actually rotating, but there are rotational forces acting on them. A rotational force is referred to, or we call a rotational force, torque. And a torque is a force, okay? Let me draw a picture here. A force being applied to an object that when the force is applied to it causes rotation. But depending upon where you apply the force, you get a different amount of leverage. So you probably understand that the closer you are to the point of rotation, the less mechanical advantage you have. So the concept of torque takes into account the fact, the distance from the center of rotation that the force is applied. But we need to understand that the force must be perpendicular to the radius. It should be relatively obvious to you if you have a force that's parallel to the center of rotation, or to the radius, then you will have no rotation, right? So it's only the force perpendicular. Now you might have forces that are not exactly perpendicular or parallel. However, they do have a parallel component. So if you know the angle, you can always determine the perpendicular component of force with respect to the radius. So torque is equal to force times radius. And the units will be newtons times meters, or newton meters. More simply put, torque, we're going to use a funky t to represent this. It's actually the Greek letter tau, is going to be equal to force times radius. Now, in equilibrium, in static equilibrium, what you end up getting is you have, like, for instance, maybe this force here is applied by an individual's weight. Now, to balance this out, if a bigger person wants to play teeter-totter with this smaller person, then the bigger person has to sit closer up because they have a greater weight. And in rotational static equilibrium, the sum of the torques has to equal 0. So we might say that all of the torques that cause counterclockwise rotation, we might call all the torques that cause counterclockwise rotation, we might call them negative. And if we add them to all the torques that cause clockwise rotation, then we will get a sum which is equal to 0, so a net torque of nothing. Now, I prefer to write this where we say that when you're at static equilibrium, the torques in the counterclockwise direction are simply equal to the torques in the clockwise direction. And that's how I put it. So we're going to use this to look at some different problems. Okay, let's look at this situation. I have placed perfectly spaced out scales pulling up on a meter stick that is completely horizontal. Now if we look at the values that are on the two scales here, we'll notice that each one of them is pulling up with a force of 0.7 newtons. Now, because of translational static equilibrium, we know that this thing is at rest. We know that the sum of the forces in the upward direction, which if you look at this is a total of 1.4 newtons, has to be equal to the sum of the forces in the downward direction. Must be 1.4 newtons. So we know that that has to be the weight of the meter stick. Now, if we look at this, we did this thing where the force is at some radius from the center of rotation, and we don't know if there's a fulcrum here or whatever, but we do know one thing, that the mass of this stick is distributed all along the stick. So if we wanted to figure out, well, where's the weight of the stick? We could cut it up into a whole bunch of pieces. Like, let's say at every centimeter, we decide to put a vector and put the mass of that centimeter at each mark. So at each little centimeter, we would make a little tiny arrow. And since there are 100 centimeters, each centimeter might have 0.014 newtons. Now, as we went along, that would be a lot of little tiny arrows. But ultimately, on average, all of that weight of that stick is, on average, at the middle of the stick. The balance point, something we call the center of mass. So we place the entire 1.4 newtons at the center of mass, and since the mass of this is evenly distributed along the stick, we put it right here at 50 centimeters. And we can do this using translational equilibrium. Alright, now so let's look at rotational equilibrium with respect to this scenario we've got right here. But first, let's get this translational little thing out of the way. We'll shrink-a-doodle it down, put it over in the corner in case we need it later. So let's say Mr. Heckman comes along and he cuts one of these two strings here. So let's say he cuts this string right here. What would happen? Ask yourself. Well, sure, obviously. The weight over here would pull down, and since there would be no 0.7 newtons pulling up any longer, this thing would rotate in the clockwise direction. So we can say that this 1.4 newtons, this 1.4 newtons is causing a torque in the clockwise direction, where the center of rotation is over here at 15 centimeters. So that means this distance right here is a total of, well, difference between 50 and 15 is 35 centimeters, which is 0.35 meters. Now we know the torque in the clockwise direction. But since I'm not cutting this string, we can say that, let's say we didn't know what this was. Let's say we knew the mass of the stick, but we didn't know what the scale read. Well, we could set this equal to the counterclockwise torque. And we could say, well, we know there has to be a force acting up. In fact, we could call it a tension, but it's at a radius of, well, this was at 15, and this out here is at 85. So a total of 0.7 meters away. And if we rearrange this, we will discover that the upward force, or the tension, correctly will be calculated to be 0.7 newtons. So that's like a basic, here's how you can use it, and here's how it predicts this very predictable scenario. So let's look at a not so predictable scenario now.